what do we mean by limiting reactant? Limiting reactant is that reactant and the reactant side. Sometimes people will call it limiting reagent. Same thing. That when consumed, he disappears, goes away, the reaction stops. The objective here is to, of course, explain that, what the definition is, but also how to determine from the data given which reagent in the reactant side is, in fact, the limiting reagent. Once the limiting reagent is determined, the calculation of product yields is based only on the limiting reagent that you determine. So having said that, we get a definition. I like reagent, but it's always on the reactant side. The problem we want to deal with is this first one right in here, and it's got a set of questions that are typical for limiting reagent type problems. So here it says number one is write the balanced equation for lead nitrate and sodium iodide. So lead 2, excuse me. Double replacement, metathesis reaction. Lead 2 indicates lead is a +2 charge, so we'll go Pb and be +2, and we'll hang a nitrate on there. And nitrate's a -1, so we have a PbNO3 2, like that. It's going to be an aqueous solution, so we'll accept that. Sodium is a +1, group 1, always a fixed charge. Iodide's a halogen, right there. I'm going to move this over some. Okay, now we want to exchange ions, so it goes to sodium nitrate and lead iodide, one of the happy halides, right? Okay, I2. So there's our driving force. Everything else is aqueous, in solution, ionized. Right there. So balancing this, we need a couple of here and probably a 2 here. So now the reaction's balanced. So that's kind of how some of the problems on the test will start. I'll give you a word, name, nomenclature of the reagents, and you have to figure out the balance of the equation. Now, number 2 in here is if I start with 25 grams of lead nitrate, I'm just going to put it together like I did, 25 grams of lead nitrate and 15 grams of sodium iodide, how many grams of sodium nitrate will be formed? So they're looking for this right here. Now again, the issue here is to teach you how to define the limiting reagent or find the limiting reagent. It's really easy once you see it. And then make your calculation based on the limiting reagent. All right. What's the first thing we do? And it didn't change from what we did earlier. Take the data and convert to what? Mole. Grams to moles is what? Divide by formula weight. Okay. 331 for lead nitrate, 150 grams per mole for sodium iodide, 85 for sodium nitrate, and 461 for lead iodide. Is that good? Okay, so The idea on the given is divide by formula weight. Here also. Divide by the respective coefficient. Well, this one is a 1 and that's a 2. So I divide this one by 1 and I divide that one by 2 and it gives me 0.076 and 0.05. The smaller value after you divide is the limiting reagent. That's true for any reaction you work. However, when working the problems, you must go back to the limiting reagent mode and work it from there. So once we've determined this is the limiting reagent or reactant, and we have 0.1 mole of it, then you work the rest of the problem like the moles of sodium nitrate will be based on the 0.1 mole of sodium iodide, not on the lead nitrate. If it's not a limiting reagent, it will be in excess after everything's said and done. We'll show you that in a minute. So if this is a limiting reagent, this will be in excess after reaction stops. But you have to go back up here and pick out the limiting reagent mole and work problem from here. Limiting reagent. I shouldn't have put the circle around that one. Okay. Because that's the limiting reagent, so we want to compare this. Two the same coefficients, 0.1 mole will produce 0.1 mole. Then times formula weight, we got it. Okay? So 0.10 mole of NaI will yield 0.10 mole of NaNO3. Yes, because it's the same coefficients. In grams, it's times the formula weight, which is 85. And whatever that comes out to be is 8.51 grams. Now, how much of the lead nitrate did we use in this thing? Well, that 2 is calculated relative to this. Okay? 2 to 1. See the 2 and the 1? Question is how much PbNO3 was used. Well, if I have a 2 in front of the sodium iodide and a 1 in front of the lead nitrate, then I have to have a smaller number over here, right, in moles. What I was telling you earlier. So if I have 0.1, then I'm only going to use how much over here? 0.05. So 0.10 mole of NaI uses only 1/2 of 0.10 mole of lead nitrate, which is equal to 0.05 mole lead nitrate used. However, problem gives 0.076 mole of lead nitrate. So if we used 0.050 mole of the lead nitrate, then excess lead nitrate is equal to the difference in those two. Everything is, once you determine that limiting reagent, everything is determined relative to the coefficient. And you figure from that limiting reagent how much is used, if that's the question, or how much is produced, if that's the question. In this case, I added an extra question in there, I guess. I don't know. What's the limiting reagent? Okay, we got that. How much non-limiting reagent will be left over from the reaction? You can take that 0.026 mole excess times, what was the formula weight of that? 331? 331. And I got a lot of these. See what this comes out. 8.6, 6 gram lead nitrate in excess. That will be in excess. Let's say you're given the following equation. It's a single replacement producing copper or basic standard state. If you start with 15 grams of copper and 15 grams of copper sulfate, how many grams of pure copper will come out of that? You got to convert those to moles, divide by the respective coefficients with 1 and 1. I'm doing this for a specific point. And then working from the limiting reagent. This is 65. Okay, so give you some formula weight numbers here real quick. So I need to convert these to moles. Since both of them have the same coefficients, then you can divide by 1. Of course, the smaller mole value is the limiting reagent. And this reactant. Now the question is, how much copper is going to? It's still a 1-to-1, so we're going to get 0.094 mole. Mole of copper produced times 64 grams per mole. So, 6. Okay, how much is in excess will depend also on this. Well, that's a 1-to-1, so how much of the zinc will I be using? Will use only how many moles? Well, 1-to-1, there's your moles, 0.094 mole of zinc. If this is the limiting reagent, the yield is based on that number as well as the excess, back and forth. And so if the yield is 1-to-1, 0.094, then the one that's going to wind up in excess is still using the same number of moles. Why? Because the coefficients are the same. Hopefully you're seeing that. But the problem says we have 0.213, so we're only using this much, so excess zinc is equal to 0.231 minus 0.094 mole of zinc. Which is 0.137 mole of zinc excess. Now, to get that into, of course, mass of zinc in excess is 0.137 mole times 65 grams per mole. Moles drop out. 8.9 grams zinc in excess. So you have to be able to deal with both of those. So there's some formula weights we'll need to got those into the problem. What's the limiting reagent? And simply how much titanium tetroxide, no, tetrachloride, titanium tetrachloride will be produced. Easy, huh? They are all that easy, provided you understand how to convert to moles and divide by respective coefficients. So we convert to moles, divide by respective coefficients. Smallest number is limiting reagent. Then we work the titanium tetrachloride yield off the limiting reagent, right? Yes. Okay, got it under control. Okay, so we want to divide by 80, divide by 12, and divide by 70. Minimize by leaving units off sometimes. Okay, 0.05. Point 0.50 and make it 0.10 rounded to that, okay? Now we divide by respective coefficients, which is a 3, a 4, and a 6. So this gives us okay. Now, I'm going to have to carry this one out like that. 6, 6. Let me do that one over again. 4.15 divided by equals, yeah, that, and that divided by 3. 17. Yeah, 173. So yeah, okay. It's kind of splitting hairs here, but technically, that's a smaller number. Is that what you're saying? Yeah, yeah. Sometimes you have to carry them out extra decimal to see who's going to be the smaller number on the end of that. Like this is pretty tight squeeze, but nevertheless, smaller value, limiting reagent. However, the 0.1 mole value for the molecular chlorine is what we have to work a problem from. So we have 0.1 going to titanium, whatever to here, and notice the number change. We go to a smaller number. So whatever you have in moles yield has to be smaller number. By how much? Half, really. It'd be 3, you can say 3/6. Okay, so I'm going to use 3/6. Because you can use the ratio. See, what you're doing is using the coefficients to scale it up or down. You know you got to have a smaller number. If I use 6/3, it's going to go to a bigger number. And you're always in pairs only. You don't have multiple considerations here. So 6/3 times 0.10 mole of the titanium tetrachloride is yield. And that's 0.05 mole 4 times 188 grams per mole. And that gives me 9.4 grams titanium tetrachloride yield. Okay. Okay, so you should have this worksheet available to you, and we'll go into percent actual theoretical yield of reactions. I'm going to put it out as I'm going to deliver it. All right, well, percent yield. Percent yield comes from the fact that in real world, no reaction produces 100% of the product that it predicts, that it will produce. So we use this thing called percent yield as a measure of how efficient the reaction might be. So it's simply a part over total times 100 issue relative to what's produced against what could be produced. And we call this actual yield, which is always less than 100% or less than what you could produce, divided by theoretical yield, which is what the equation predicts you could get in a perfect universe, and then times 100%. Now, it might be helpful to make these notes. Actual yield, I call sometimes the lab yield. You run a reaction in the lab and it's going to give you a certain amount. Well, that's always going to be less than what you theoretically could produce. Theoretical yield is what's calculated from the chemical equation. Calculated yield. From the chemical equation stoichiometry. Typical problem will give you how much the lab yield is. And focus is going to be on, well, you calculate the theoretical yield and then apply it to the definition of percentage. Okay? Just setting it up so you save you some effort. But this is what you need to do anyway. You need to go write the equation, balance it, and then put the formula weights above the reagents that are in the equation so you can convert to moles and make it a little easier. Okay, so this one says, I began the reaction with 20 grams of lithium hydroxide. All right, 20 grams. What's the theoretical yield of the lithium chloride? Okay, so they want this in grams, and that'll be theoretical. Just to make a note of it, and that's what they're looking for. Well, you want to convert to moles, divide by 24 here. And that's 0.83 mole of the lithium hydroxide. And so since the coefficients are the same, 0.83 mole of the lithium chloride will be produced. And in grams, that will be times 42 grams per mole. And that's 35, grams of the lithium chloride. Okay, so this is the theoretical yield because it was calculated from the equation. And I think it goes on next. I actually produce 6 grams. It's equal to 6 grams. Okay, sorry. So the percent yield is actual over theoretical times 100%, which is 6 over 35 times 100%. Let's see if I get close. I got 17%, roughly 17.1%. I don't know what. He got 16.9, but throw in the significant figures, probably adjusted. But the problems work the way it's supposed to work. All right. Okay, so here's our propane, 44 grams per mole, 32 grams per mole for O2, 44 grams per mole for CO2, and 18 grams per mole for water. Just for the formula weights per mole, one formula weight. All right, let's see what it's going to. Start with 5 grams here, given. What's theoretical yield of water? Over here. Well, what we do? What's 1? Convert to moles. Thanks. Divide by formula weight. And 5 out of 44 is Okay, so we got a 1:4 ratio. Will the number be bigger over here than what I start with, or smaller?
Bigger.
Bigger. See, I got a 1 here and a 4 over here. So whatever I get over here, it's got to be bigger than 0.114. By how much? 4 times. That's right. It's actually 4 over 1 times 0.114 mole. Once you see that, you can work all the stoichiometry problems. You just say, well, I got to have a bigger number. How am I going to get there? I'll take a ratio that'll make it bigger. Make it easy on yourself, guys. So the water yield is theoretically 0.455 mole theoretical. And if you want to go grams times 18 grams per mole, I get 8.18 grams. Theoretical yield there. What did they give us on the actual yield in there? I got a percent yield of 75%. How much water did I make? Okay. Well, you could use the percent equals actual over theoretical times 100% solve for the actual. Okay? So if he got 75% yield as actual, theoretical 8.18 grams times 100 and solve for A. Everybody good? It's just a one variable algebra problem now. So let's see, that's 75 over 100 times 8.18 grams. So that is your actual yield, and that based on the data that's given in that problem. So there's numbers that we can get started with. So we want to convert to moles, and then solve for the grams of iron chloride here. So divide by 216. And I have 0.157 mole. You look like a 7. Of the iron bromide. Yeah, I was hoping for multiples, but that's not what they gave me. So that was going to give us a 0.157 mole theoretical yield. Because coefficients are identical. Okay? And grams, that's times 126 grams per mole. Convert it back. And that's 19.83 grams FeCl2 theoretical yield. Actual yield is 4 grams. And this gives us a percent yield, actual over theoretical, times 100%, 4 over 19.83 times 100%. What can I say? Too easy, huh? That looks like 20.2%. So 20% here, something like that. All better.